Alright, 6.4, we're going to add dot products to our knowledge of vectors. So here's our definition of the dot product. So for the first couple of examples, we're just going to use the dot product without really understanding what it does, because the dot product is just really a mathematical tool that will lead to other things. So for right now, let's just understand what it is. Okay? When we have the I and the j parts, the component forms of two different vectors, the dot product of those vectors is multiply the I parts together, multiply the j parts together. Let me skip this and come back to this. Find the dot product of these. The dot product on A is multiply the 4 times the 2, add, multiply the 5 times the 3. 8 plus 15, we get 23. Multiply the i's together, 2 times 1. Multiply the j's together, negative 1 times 2. 2 minus 2, the dot product is 0. Multiply the i's, 0 times 4. Multiply the j's, 3 times negative 2. We've got 0 plus negative 6. We've got negative 6. All right? So, really quickly, let me jump back here. Some properties of the dot product. So, it is transitive. Okay? It is, sorry, not transitive. It's commutative. Okay? It works both ways. If we times by 0, we get 0. Okay? We can distribute in. If we times it by itself, we get the magnitude squared. So this is one that actually will come up more often than not. Okay? The dot product of a vector with itself is the magnitude squared. Okay? So we see that one a bunch. So anyway, now that you've seen how to do the dot product, find the dot product between these two vectors. All right, now let's find the dot product and then do some multiplying here. So let's see what the dot product times vector w is going to be. So the dot product of u and v is going to be negative 1 times 2 plus 3 times negative 4. And we've got negative 2 minus 12, so negative 14. So I've done this part so far. I've just done the dot product, negative 14. Times w still. So w is the vector 1, negative 2. So if I distribute that negative 14 in, I get negative 14, comma 28. And that would be my answer for the dot product of u and v times vector w. All right, what about the dot product of u times 2v? So really quickly, 2v is going to be 4, negative 8. So the dot product of u and 2v, come back pen, there we go, is going to be negative 1 from the u, 4 from the v, plus 3 from the u, and negative 8 from the 2v. Negative 4 minus 24, negative 28 is our dot product. Your turn. See if we can put them together. U and V do the dot product times V. All right. The dot product of U with itself is 5. What is the magnitude of U? So let's jump back into that formula we had. Dot product of U with U equals 5. And remember the formula for a dot product of a vector with itself is the magnitude squared. So we can say the magnitude squared equals 5. Through substitution, we'll square root both sides, and we know the magnitude of u must be the square root of 5. Okay? So remember, the magnitude of a vector with itself is the dot product of a vector with itself is the magnitude squared. All right, so do that with 25. Okay, so now we finally get to actually use the dot product for something pretty useful, and the useful part is that if we use the dot product divided by the magnitude of the two vectors The answer is the cosine that's in between the two vectors. And this is very useful. It comes up quite a bit. Okay? So make sure you have this formula down in your notes. And then let's go ahead and use it here to find the angle between these two vectors. All right? So first we need to find the dot product. 4 from the u, 3 from the v, 3 from the u, 5 from the v. Okay? And so that's going to equal 12 plus 15, which is 27. We also need the magnitude of u, which is the square root of 4 squared plus 3 squared. This is a 3, 4, 5 right triangle. And the magnitude of v, a little messier. Square root of 3 and 5. So that's going to be, what do we have here? 9 plus 25 is 34. Okay? All right, so the angle between them, cos theta, equals the dot product, which we've already figured out is 27, over the magnitude of u, which is 5, times the magnitude of v, which is root 34. All right? So we would want to, if we were trying to simplify this, rationalize the denominator, but we're just trying to figure out theta here, so we can just do our arc cos of 27 over 5 root 34 in our calculator and let it spit out an angle for us. So I'll go ahead and do that. Grab the calculator and make sure I'm in degrees, which I am. And so we're going to go inverse cos of 27 over 5 root 34. And our answer is going to be, oops, what did I mess up here? Oh, my parentheses. 27 divided by 5 root 34. There's my problem. There we go. And let's do the cosine of that. 92609. And 22 degrees is going to be the angle in between those two vectors. Okay? All right, so you're up. Use the same formula to find the angle between these. Remember, this is 2 comma negative 1. This is written in component form. All right, so let's take a look at a couple things here. If we rewrote that formula and got the dot product equal to the magnitude of u times the magnitude of v times the cosine of theta, okay, just rewriting the formula we already had, okay, what we have here, this is the alternative form of the dot product, that the magnitude of u and v are always positive, okay? The dot product will always have the same sign. So what that's saying here is that if the angle is 90, the cosine is going to be 0. If the angle is acute, the cosine is going to be between 0 and 1. Okay? If the angle is obtuse, the angle is going to be between 0 and negative 1. Remember, we can't do inverse cosines bigger than 1 or negative 1. So if it's negative, will be obtuse. Positive will be acute. If we get 1, we're going to have the no angle in between them. And if we get negative 1, we're going to get 180 in between them. And this is all coming from the values of cosine on the unit circle. All right, so something that's helpful, don't have to have this memorized, but it is something helpful just as a check. But the one that comes up a lot is this one right here. How do we find out if something is a right angle? Well, if the dot product is 0. And a phrase we have for that is orthogonal. So u and v are orthogonal if the dot product is 0. Orthogonal and perpendicular mean the same thing. Okay? So we meet at right angles. So are these two vectors orthogonal? Let's find out the dot product. 2 and 6 plus negative 3 and 4, that's 12, and negative 12. That adds up to 0. So yes, orthogonal. If the dot product is 0, back pen, there it is, then yes, we are orthogonal, which means that those two vectors are perpendicular and form a right angle. tell me if these two vectors are orthogonal. Okay, so we already did this. We looked at this boat problem here, okay, and kind of broke things down into pieces, right? And we also looked at a couple of problems where we had multiple vectors pulling on a single object, right? And so what this whole thing is saying is it's helpful sometimes to take a vector and break it down into different pieces, right? The sideways piece, the up and down piece. And what that's called is called projecting one vector onto another. Think about it this way. Think about if I had some object and I was pulling on it in this direction, right? So I'm going to redraw this graph here. I'm pulling on it, okay, in that direction. Now what happens if your buddy came along and your friend also grabbed it and helped you, but he was pulling in this direction, okay? You really want to go that way, right? It would be really helpful if your friend was lined up in the same angle as you, but for whatever reason, he wasn't that helpful. He was helping you pull in this direction a little bit, right? Because this one has a little bit of that piece to it, okay? But he's not helping you as much as he could be. Our job is to figure out how much is he helping you? How much is he adding in the direction parallel to the direction you're already going? And what that's called is called the projection. If we take a 90-degree angle down to your original vector and just found the piece that's being added on, the helping part, okay? The formula for doing that is right here. The dot product over the magnitude squared times the original vector. All right, so we're going to do that formula here. So dot product first, 3 and 6 plus negative 5 and 2 is 18 minus 10, which is 8. The magnitude of v is 36 plus 4, which is 42. And since it's squared, it's 42. So my dot product was 8. That's the top of the formula. My magnitude squared was 42. Okay? 8 over 42, they're both even. That's 4 over 21. Okay? Times the original vector, 4/21 of my original vector, 6 comma 2. All right, so how much did this help us? And let's just do the calculator real quick. 4 times 6 divided by 21, and 4 times 2 divided by 21. So 1.14 and 0.38. Okay, so that's okay. So if instead your friend who is helping you pull this, okay, moved in the same line as you, okay, he would have helped you pull that rope that far to the right and that far up, okay? Even though he was pulling 3 and negative 5, if we rearranged him and just got the force that's going in that direction, it would be this much, okay? That's the projection, the piece that lies parallel. See if you can use the formula and see if we can find the projection of u onto v. All right, follow the formula very carefully. See if you can get the component form of this. All right, so let's find force here. So we've got a 200-pound cart right here sitting on a ramp that's inclined at 30 degrees. And so what force is required to keep the cart from rolling down the ramp on this one? So let's see what we have to do to hang on to this thing. So right now, we've got 200 pounds going down. Okay, we've got a right angle. And we know 30 degrees is here. So if this is going to be a right angle, then this is also, let's see, so this is going to be 60 in here. So this one would be 120. 20 in there, and so your 60 is also right here, and so your 30 ends up being down there. So we've got 30 degrees down here. Okay? All right, so let's see if we can figure out the component force to keep this thing from moving down the hill. And so we want to find this piece right here. We'll call this W1. Okay? All right, so what we're looking for here is the projection. Oops. Projection's not spelled with an F. The projection, right, of something onto something else. So we're projecting the part of F, right? And we're projecting F onto the original vector here, V. We're projecting F onto V. So let's see what we've got here. The formula would be the dot product of F and V over the magnitude of V squared times the original vector V. Okay? So on this one, we know, oh, hold on one second. Sorry about that. Okay, so we need to see if we can figure out what the F and the V vectors are. So let's look at F first. F is going straight down with 200 pounds. All right, so that's going to be 0I, and it's going to be minus 200J, or we could write it as 0, negative 200. Right, that's our F. It's going straight down. Let's think about V. V is going in this direction. Okay, it's got an angle of 30. And so let's see if we can figure out what the I and the J forms are. The X and the Y's here. Okay? So on this one, and it has a vector of 1. Do we have that? Yes. All right. So we've got the sine of 30 for the J, and we've got the cosine of 30 for the I. All right, putting them together here. So that turns into, this is your F, and this is your V, and so we've got here, cosine of 30 is root 3 over 2, and sine of 30 is 1/2 for J. So we put these in here. Let's figure out the dot product first of all. The dot product here is going to be 0 times root 3 over 2. So that goes away. And then we're going to say negative 200 times 1/2. So the dot product is going to be negative 100 over the magnitude here is going to be V. If we have this, this is root 3 over 2 squared plus 1/2 squared. This is from your unit circle. That's going to turn into 1. So just 1 in the denominator times the original vector here. Okay, so if we plug this in, we've got negative 100. Our original vector came from here, turned into V, root 3 over 2I plus 1/2 J. That is the big one. All right, that's putting everything together. And remember I said that these kind of incline problems are going to be an extra credit type thing. But if you followed that all the way through, see if you can figure out how to do 75. All right, good luck on this one. We will definitely go over 75 in class as well. All right, there's the solution if you got all the way through. All right, last thing here, let's look at work. The work done on anything is defined as the projection of F onto your distance from P to Q, okay, and the magnitude of that, and then times the magnitude of PQ, okay? And so the alternative form is the vector F times, with the dot product of PQ here, okay? So PQ is just the original direction that you're pulling it in. All right, so let's figure this out. And we've got a barn door, and this person attaches a rope at the top, pulls down at 60 degrees. He's pulling on it with a force of 50 pounds, all right? And we want to find the work done in moving the barn door 12 feet here, okay? All right, so this is actually more straightforward than it seems, because what we want to do here is find the cosine of 60 would give us this distance right here, okay? And that distance times this length, the hypotenuse, which is 50, is the projection of the diagonal back onto this direction, okay? So then we just need to times it by the original PQ, which is 12, and so the cosine of 60 works out very nicely to be a half times 50 times 12. Half of 50 is 25, and 25 times 12 works out to be 300 exactly. So we are doing 300, and then the unit on here is, this was feet, and then 50 pounds of force. So the unit is feet pounds. You are doing 300 feet-pounds of work. All right? Go ahead and see if you can use the exact same type of thinking for 79. Get your answer there, and you are done with 6-4.